Okay, so in my last video, I just reviewed what we did in the previous class. So now we know how to calculate the sum of square regression and sum of square residual, and we know what they are. And okay, now we want to talk a little bit about standard error of estimate. What that is that when you create a regression model, it is common to report a standard error of estimate. Standard error estimate gives a measure of the typical distance between actual outcomes y and predicted outcomes y. In other words, it gives a typical amount of error in a prediction. Prediction and the actual outcome are usually different, and so there are some differences between those two values for each x, for each x value there's a y value, and there are differences, and the typical, so in other words, it's just the average of those differences. That's the standard error estimate. Let's take a look at this. So standard error estimate is calculated as follows. SEE stands for standard error of estimate, and as I say, standard error estimate is it's the average of all the differences between the estimate and actual outcome. And how you do that is this. When I say average, think about you get the so these are predicted values, but for example, when second starts at 0, predicted value is 83 or something, for example, but you might actually get higher or lower exam grades. So that's going to be the difference. And for each value, you get that error, the range of errors. Okay, for this you might actually get 120. For this you might actually get 110, for example. And those there, so for each predictive value, you get one value you can get is an estimate, but actual outcome are usually different. So the difference, for each value here, you get differences, a difference between the actual outcome, and expected value. So those range of or amount of error, so there's always a range or amount of error for this expected value and outcome relationship, pair, and the standard error estimate is just the average of all these errors. So typical value, typical amount of error you might find in this, that's the standard error estimate. And so logically speaking, okay, so that's what is that? That's residual. How you can do it is the residual. Because the expected value is this. Those dots that creates this line in expected value. For 0, it's that. For 1, it's that. But actual values are these dots. So the difference is actually residuals. And how you can do it, so you calculate these, you add them up and divide by the number of the x values here. That's how you logically do, but because it's statistics, you can have to consider this margin of error. Usually, when you use sample, there's some there's a room for error always, and by subtracting 1 for each group, you usually get a fair amount of estimate. And in this case, because we have 2 variables, so we subtract 2, and then we get a fair amount of fair estimate for this. What we do is, because we are considering the actual amount, basically what we get these distance and then get the average, difference between the expectation and the actual value. So you get these distances and average them up. That's what we want to do. But when you calculate it, when you just get the differences, sometimes you get minus, sometimes you get plus, and it's hard to calculate with the plus and minus because they're going to cancel out each other. So that's why you use squares to get the positive number, get the distance, or turn it into a size. In other words, when you square, it turns into an area. So it gives you a size. Always gives you a size, some size. That's why we're using the sum of square for residuals instead of just using the residual, which is just a distance. So it's just a line value. It's a distance. It's a distance, just a distance. But when we use the sum of square, we're actually calculating because it's a square, this times this. So it's like getting the area of this square. Okay, so we get the square for each these. Then we average them up. What we get is, though, without this square root, what we get is the average of the areas, not the residuals, not the distances. What we get will be average of all these square area. So it's not gonna be the distance, pure distance. It's not gonna be the average of all these pure distances. So what we need to do is use a square root, and I'll bring it back to one-dimensional distance from the two-dimensional area. That's what we do. Does it make sense? It makes sense to me. So again, when n is a number of pairs of, so okay, so well, that's fine. So let's calculate that. Sum of square residual was 4,862.22, and the odd observation is that there are 15 pairs. That means we subtract 1 from each variable, so 13. And if you use a calculator, and you get 19.34. So that's standard error estimate. That's a typical amount of residual or errors you find from this estimate. So the typical amount of error, so this error, this is also error, this is also error, this is also an error, this is also an amount of error, this is also the amount of error. So average of all these is 19 point, oh, what's that, 82? 19.34. See, for this, it's error, the distance or the amount of error is, because this is like 28 and this is actually 68 or something, so 40, but this error is probably about 10 or 8. and this error is only like a 3 or 2, and this error is about 12. So the average of these errors is about comes down to 19.34. That's what we calculated by using this method, sum of square residual divided by the n-2 and get a square root, because this would just give you an average area, so turn it into distance. That's what we did. So that's how you do calculate the standard error estimate. The standard error estimate is 19.34, and typically predicted exam grades are off by about 19 points. That's typical, more logical and practical interpretation of standard error estimate. And funny thing is, that's all that, and we're not going to use this value for anything else later on. Just if asked, you need to give this value, standard error estimate. And as I said, it's typical to present this value as the other values when we do this regression, when we report regression model. The next we're gonna talk about hypothesis testing of regression. What that is that we do analysis regression to determine if the predictor X in a regression model explains a statistically significant portion of variability in the outcome variable. Because all we did was all the calculations and coming up with the percentage of the regression, what should I say, accountability or reliability of the regression model. This regression model will explain how many percent of all the variability. That's the only thing we did. What we didn't do is, we know how much it explained, but just like ANOVA, t-test, Z, and all the other, what we didn't do is, okay, so what's the critical value? How many percent is the actual in other words, what we'd like to prove is that if okay, for example, if you get like 56%, it explains that 56%, for example, and 56% is that a statistically significant portion. Is it explaining the statistically significant portion? In this example, you get the statistical reports like this regression model explains 45%. This regression model explains 60%. Then we need to determine if those numbers, 50%, 45%, 60%, is it actually explaining the statistically significant portion. So in other words, we need to find out what's the typical amount of the ratio percentage that the model has to be able to explain. And so we get that value, and if it's explaining more or less, then you kind of figure out if the model is good or not.